talking about some work that I've been doing on basically building plans with opportunities in them, so you can achieve more if things are going well. So, just a very brief introduction to planning. Obviously this is a planning session. In theory you will all know what planning is, but just in case. So, the reason I wanted to put this slide in is to emphasise that this is generic. So, we have an initial state, and that can be specified as a set of predicates and assignment to numeric fluids. So, it's an arbitrary problem. It's not, we're not solving a specific problem. I'm going to be very example heavy here, take you through an example problem, but everything I talk about is generic. So you specify your initial state, you specify your goal state, and you have actions which have preconditions. If they're satisfied by your state, you apply your actions and you get their effects. And the challenge is to find a sequence of actions to transform the initial state into some state that satisfies the specified goal. So the motivation for what I'm doing specifically here is that we have resources in the world, but they're generally limited or hotly contended. And what happens in safety critical applications is that generally we plan in a very conservative way. So we say, we'll assume the worst, we'll assume everything takes 99% of the possible time it could, and then our plan will never fail. And a particular place where this is really bad is in space operations, which is why we've got a nice pretty picture in the background. So in, for example, Martian rover problems, they say they restrict very much what they can do in order to be certain that the rover will remain safe. And in many situations, replanning is not always possible or desirable. So if you've got radiation-hardened hardware, you can't always use that to replan. Planning is a big combinatorial search problem. You can't do it on Mars. And also, interestingly, it's not always desirable. So people are very conservative in space. They don't want you to plan. They want to know what their rover is going to do and know that it's going to be safe. So they won't let you replan. Yeah, we're working on it. So, but that doesn't make good use of the resources available. So the Sojourner Mars rover actually spent 50% of its time sitting there waiting for instructions to be safe. So the question is, how can we do better? How can we make the most of our available resources while still satisfying these people who want to be very conservative about the resource usage we're going to have? And what we can do is we can make use of our knowledge at execution time in order to decide what to do in the future. But somehow we want to do that without knowing that execution time. So we want to generate this plan a priori. So this is a slightly more formal version of the problem. It's an oversubscription planning problem. So we have soft goals. Each goal has a cost for non-achievement. So whenever I say today maximising utility, it's synonymous with minimising cost. So I will use those terms interchangeably. We have uncertainty about how much resource each action uses. This may be the energy used for the action, it may be the time the action takes to execute, or it may be the change affected by moving a certain component or something. And we ask that you specify a continuous distribution of values. So you can specify your own arbitrary distribution. And we have these constraints. So these are our safety constraints. Whatever resource it is, or whatever measurement it is, must be greater than or equal to some threshold theta with a given confidence level. This can also be less than or equal to, either way, it's interchangeable. And this condition must hold at every point during plan execution. So it's a safety constraint. And what we're going to do is build branch plans. So traditionally plans are linear. Do this, do this, do this, do this, do this. Whereas we're going to build branch plans with conditions which you can choose at execution time which branch should follow given how much resource level you have available. So this is the basic concept. We're going to plan pessimistically, assuming that actions will have high resource consumption. So we're going to say, right, everything's going to take 99% of the longest possible time it can take, And we have a planner that can do this. It's called LPRPGP. You don't need to know how that works for now, just assume we have it. It's another paper in itself, it's an ICAP 2011 if you're interested. And we give it the metric to minimise the cost of the unachieved goals. And these are standard in the PDDL3 language standard constraints. So we say the constraint that whatever variable we're concerned about has to be greater than or equal to 0. And now if we're going to build extra branches onto this plan, so create one plan, we're going to build extra branches on the side that gives opportunities of things to go better than expected. Which, let's face it, they probably will, because we've just planned with assuming the worst. So we're going to plan again from states along that plan. Again, using exactly the same planner. Assuming a lower energy consumption to that point. And that will, maybe we'll be able to achieve some more goals. The two big questions here. Which states do we plan from? Along the plan, we can plan from all of them. That's going to be quite expensive. On what energy consumption do we use for the plan header and for the new plan? So what assumptions do we make about how well things have gone? So there are two questions that I'm going to answer later. And the question is, the research questions here is, will this allow us to achieve more than just a pessimistic plan? Will it allow us to achieve more than online replanning? So online replanning is sort of our goal here, well not our goal, our target. It knows exactly what's happened, so it's always going to be better, but how close can we get to it? And of course, will we have a lower success rate? And by success, I mean this constraint is not violated. So, very quick, non-related work. We're not the only people interested in this kind of problem. People are trying to solve these problems with MGPs, which give a kind of an optimal expectation maximization idea, but they're very expensive, they're very big, they're good scale as well. This is perhaps the most related piece of work from ECAI 2010, that is actually. And that is going to about how to create a linear plan in the presence of uncertainty. So we're kind of building on top of that. Other people have done branch planning, but in the propositional case, so not continuous resources, but only based on propositional uncertainty. And people have considered it in scheduling. Other people have looked at how to execute this sort of plan when you've got it, which is obviously good for us. And there's obviously a lot of work related in the soft goals and the deterministic settings. So on to our example problem then. Taking a rover's domain from IPC5 is the oversubscription variant written by Patrick Haslam. And what we have is basically it's a rover moving around Mars, it can navigate, it can take soil samples, it can take photographs, etc. So we've modified it. So each navigate action, instead of just having this traverse cost, which was fixed in that domain, we use this traverse cost to say how much energy it will use. So the energy used is equal to the traverse cost, well, a normal distribution, with mean equal to the traverse cost, which is just a function of distance between the two, and we set the standard deviation to the mean, just to give us some kind of... So this is quite a lot of uncertainty, but that is fairly realistic in a rover setting. You really don't know how long it's going to take and things are going to go wrong. So we have a constraint that the energy of the rover is greater than or equal to 0 at all times, with 99% confidence. We're very concerned about this. And that's just the details for anybody familiar with the rover's domain. We've taken some traverse cost out because that is now captured by our energy constraint. And our goals are all soft goals. So they all are goals, we can achieve them or not, and we pay a cost if we don't. So here's a linear plan that our planner will produce for that domain. Now when we're building this plan, we have a number of questions. How do we build a plan that executes with 99% confidence? Well, we're quite lucky because we have this approach of RTU, and we can actually build this plan using a similar approach to them. The big question is action applicability. So say this action here, communicate soil data, has a precondition that energy is greater than or equal to 20. How do we decide whether that's satisfied? Normally that's easy, we just look at how much energy these things take. But in this case, we don't know how much energy these things are going to take. So there are two possibilities. I'll do them in reverse order. So if your Bayesian network is analytically solvable and you want to plan to 99% certainty, then it's admissible just to take the 99th percentile from that Bayesian network and say, well, if I can execute this, if this is satisfied within 99% certainty, then I'm not going to prune any solutions that would have done better than 99%. So that's the first way. But if your Bayesian network can't be solved analytically, you don't want to simulate a Bayesian network every time you want to apply an action because that's very expensive. So instead we just say, we'll use the mean. And when we get to the end, once we've generated the plan, we then simulate it with the Bayesian network, and if the constraints are not valid to the requisite confidence, we just throw it away. So that in practice is faster than actually running the Bayesian network at every point in search, even though we had to throw away some solutions. So now to move on to building branches. Remember the question, where to build branches? Do we build them at every action in the plan? Well, there's actually no point. We only need to build them at actions with uncertainty. Now in our example, we've only actually got uncertainty in the navigate actions. And you might say, well, that's not realistic. You probably have uncertainty in soil samples and sampling soil and dropping from the soil. But in practice, there is much more uncertainty in navigating versus these actions. So it's safe to assume that we can say that those have no uncertainty and plan with those, because relatively speaking, they are much less uncertain. So we'll only need to plan for any action with an uncertain effect, because otherwise we're wasting our time. Nothing's going to have gone better than expected if there was no uncertainty in what would happen. So what is the initial state now for planning? This is the question of what do we assume has happened so far. So we're going to assume all actions that happened so far have had their mean effect. So before, they had to have their 99th percentile effect, or this whole plan had to complete with 99% certainty. Now when we're planning from a certain space, say we're planning from here, all this only has to have executed to 50% confidence, but the remainder must still execute with 99% confidence. And then we're going to try and build a plan from this state, and it happens very nicely that the planner we're using has very good pruning heuristics. So, and this is critical for this application. You've got to have a planner that can quickly tell you, no, there isn't a solution if there isn't. Otherwise you're going to spend hours searching for solutions that don't exist. So let's try planning then. So navigate actions have uncertainty in them. So can we find a plan here after this navigate action? Well, no, because we've not had enough time. We've only done one navigate action, so even if that goes to 50%, that doesn't give us much more energy to deal with. We'll carry on going down. Again, we can't find a plan there. And at the next navigate action, we find we've got a plan. So, from this state, if this lot consumes 50%, or its mean amount of energy, then from here, we can, with 99% confidence, execute this plan and get down to a cost of 76.5 versus 160. So now what we're going to do is we're going to recurse on the branch. So again, can we do anything better from here? No, we can't. Can we do anything better from here? No. Here. Carry on. And eventually we get this other plan from here. We can actually get down to cost 0. So that means we've achieved all our goals. So then we're going to recurse on the new branch. And actually, obviously, we're never going to do any better than 0, because 0 is no cost. So we're not going to find any plan from here. So once we've done this, what we then want to do is merge the branches. Obviously, you can see there's a lot of duplication. This plan here is the same as all this plan here. And here we've got some duplication too. So we're on this branch. We want to, all we're going to do to merge is quite a simple algorithm, is go along the parent branch and the new branch, and while the actions are the same, these two are the same, merge them together. So those two actions are the same, and we can merge them together. Now this does have some limitations. If there were any permutations of this plan which weren't important, so the ordering wasn't important between two steps and they were different, that would stop us from merging. unnecessarily. And it would also be possible to do more sophisticated merging to create DAGs. So for example, if this action were different, but these were the same again, we could not merge, we could have a merge back in again after that. But we don't do that. We've not found that our policies are too big in practice, but there's lots of stuff to be exploited there. So now we've got this merged branch here, we've got to answer the question, which way do we go when we get to here? How do we know which branch to take? And we get the answer again by going back to our Bayesian network. We look backwards through the plan. And this takes 0 energy, this takes 0 energy. This here has a normal distribution of energy. So we build up our Bayesian network backwards with those values, and then we sample it to find what's the 99th percentile of the energy usage of this plan. And that tells us if you have greater than 354 units of energy, then you can complete this branch with 99% confidence. And we do the same for this branch, the original branch, exactly the same process. And you can take this branch if you have 219, and these other labels here are the cost you achieve if you take that branch. Now we've returned from this recursive call, so we need to carry on down this branch. Can't do anything from here. So now we're finished on this branch. We're going to merge these two branches. As you can see, there's a lot of stuff the same. And we have this structure here. And finally, we need to carry on down this branch. There was nothing from there. So again, we're going to back the labels up and compute the necessary energy for this branch. So one thing you might have noticed when I was doing there is I've actually now put a label, a condition on continuing with the original plan. And this is a matter of execution semantics. So you have two choices. You can either do our standard execution semantics, which is just take the lowest cost branch, so use these cost labels here, for which a condition is satisfied. And if you don't put a condition on the original branch, because that was what we were doing in the first place, we were just building a single plan, then you will always continue down the original branch, and you will only take these if you get better energy, but you'll never stop here. Fail-safe is a slightly more conservative execution semantics. You can terminate your plan at any point along here if this condition is not satisfied. And you can build your conditions right up the plan so that you can stop at any point here, you can truthfully work them out. And so those are our two execution semantics, fail-safe and just the standard. So we've done some experiments with this. We have a time cut-off for generating initial plans. So our plan is not optimal. It will search to optimize, and we give it a certain amount of time, and we want the best it can do in that time. We also have time cut-offs for branches as well. We're going to use both execution semantics, and this is the reason we've considered two different ones. So the failure rate is comparable to the linear plan, so the original plan, using the standard semantics. So if we just carry on regardless on the linear plan. If we want it to be comparable to a simulation of online replanning, we've got to use these fail-safe semantics, because online replanning will not find a plan if there isn't enough energy. So we need to make sure at every point before we execute our branch plan, we make sure there's enough energy to continue. So that's why we have these two different lots of semantics. Our simulation of online replanning, we did 1,000 runs. Ideally, we'd have liked to do some more, but it really did take a very long time to run, so that was the best that we could do. And online replanning, as I said, is like the gold standard. It knows exactly what the state is at the time you want to branch. So you say, this is my state, where can I get now with 99% certainty? So it definitely is a sort of oracle that we're aiming for. And as I said, this is generic. And to demonstrate that, we've tested it on 3 domains. We tested it on rovers, which I've been discussing before, AUV, which is autonomous underwater vehicles, They're doing cleaning operations and observations. And the final one, which is quite different in structure to the other two, is the transformer domain, which is the domain that we generated with engineers. And what you have to do is regulate the voltage at a substation to be between an upper and lower bound. And that changes because customers are varying the demand they use during the day. And so you have to use your transformers, set them up, set them down in order to keep the voltage correct. So we decided on a quite a short time for initial planning and branch planning. So this is the time to generate the initial plan. We use 60 seconds to generate the initial plan. And just to prove to you that we're not crippling the planner by not giving it long enough to generate the initial plan, here's what happens if you use 900 seconds. You don't actually get very much better plans in these two domains at all. Here, you get slightly better plans for the larger problems. But in general, we're not crippling our linear plans by using this shortcut. So we use 60 seconds for generating the initial plan, and then we allow it just 10 seconds to generate branches, which we'll see later. So, these are graphs of a linear plan given 900 seconds, linear given 600 seconds, and branched with 60 for the initial plan, 10 for the branches. And this equivalent linear plan here is just because the branch plans have slightly different failure rates to the linear plans, because we're taking more risk. If things are going better, we're going to do a more risky thing. So this is the utility, the cost of the branch plans in yellow, and you can see that they've actually got much better utility than the linear plans. Even if we give the linear plans 900 seconds instead of the 60 we've got here, and even if we make the threshold slightly higher for uncertainty to make sure they're directly comparable. So that's a very good result. We've got more utility. And our failure rates, obviously they're slightly more risky, so we get slightly higher failure rates. But you can see these green lines here are the actual cutoff. So we asked for 99% certainty. So this is the 1% failure line, 1%, and these are actually done to 95% certainty. So this is 5%. And the branch plans sometimes exceed that failure rate because theoretically we're only taking 99% out at each point, so it doesn't quite make the 99% out, but you can see it's generally under it and it's very similar. If you were desperately bothered about you had to be at the 1% limit, you could always change your threshold to 0.9 and try generating your branch plan again. We've not got an analytical way to do that, but you can actually always get a plan that's reasonably good confidence. And this is kind of the big headline result. If you take away one thing from this, this will be it. So branch plans cannot obtain most of the improvement we get between a linear plan and online replanning. So the cost of the branch plan is 64% of the cost of the linear plan. And the cost of replanning is only 54% of the cost of the linear plan. And this is an average across these three domains. So this is a geometric mean of the ratios between the cost of the branch plan and the cost of replanning versus the cost of branch plan and the cost of the linear plan. So we really are getting a good chunk of the benefit of online replanning versus taking a single plan by doing this branch plan. Okay, last page of results. If we use the fail-safe failure rates, so I should have said these are with the fail-safe failure rates because we're comparing to replanning. So we've got very much less than the 95% confidence threshold we asked for all the plans. So for the branch plans, I've not shown the transform domain on here because the failure rates are all 0, so it wasn't worth drawing a graph. But you can see here 0.6% failure, less than 0.25% failure. So just by doing this extra check at execution time, your branch plans are always within the failure rate you asked for, which is fantastic. And the failure rates are relatively comparable. There's no massive jump in failure rate for going to a branch plan versus a linear plan. And that just about wraps it up. So we can build branch plans using a standard forward chaining planning approach, and that allows us to decide execution time, which branches to execute, and we can get a lot of the utility we get by online replanning